We start New Manufacturing Seminar, the medical equipment version. This is a 15 minutes video introduction. Let's begin. First of all, let us explain about the medical equipment market. In recent years, the medical equipment field is the world's fast-growing market with the aging population and with the population growth in emerging countries. It is anticipated to grow around 25% from 2010 to 2015. There are various types of medical equipment used for all stages from diagnosis to treatments. Completely different manufacturing are required for each type. And today we have selected 3 typical equipments to propose our new manufacturing. The most important theme in manufacturing is being efficient through skill-free processing and cost reduction, and also shortening of the total lead time. Let's start with the characteristics of each product. First is the clinical chemical analyzer. The top part is the display section, and the bottom part includes the control system such as the power source and the circuit boards, as well as the drive system. It consists of aluminum partitions, galvanized steel frame, and small complicated brackets for mounting motors and sensors. Half of the material used are galvanized steel and stainless steel, and aluminum are also used. Many plastic parts compose the top exterior cover. Next is the X-ray CT scanner. Inside of the distinctive R shape, we find galvanized steel sheet metal structure frame and aluminum machining processed frames. It also has control box and detection unit with many rivet structures. Galvanized steel is the most used material, and structured steel is also used for the cradle or bed parts. Stainless steel and aluminum are hardly ever used. The exterior cover uses many plastic parts. Last is the artificial dialyzer. The inside is a 3-deck structure frame consisting of power source, piping, and a base. All parts are integrated and its characteristics are sophisticated shape with many bends. Assembly is done mostly with crimping and spot welding. Work efficiency is promoted by temporary assembly with the rivets, then spot welding. Material used are mostly stainless steel. Plastic is used for the exterior cover. We have interviewed Dr. Fumihito Yoshi of Tokai University Oisu Hospital, who actually uses these instruments to learn the needs of medical equipment in general.
最近病院内では患者さんの気持ちを和らげるように優しい色使いや R 形状のデザインを採用しております。同様の理由から検査機器なども同じようにデザイン性を重視しております。また患者さんの負担を軽減するためにできる限り移動せずに検査を受けていただくように運搬しやすい軽量化や小型化された検査機器を選んでおります。病院も差別化が必要な時代ですので、備える検査機器には先進性の高い機能を備えた最新のものが必要です。今後医療機器の更新需要は高まりますが、設備導入のためにはイニシャルコストの低減が重要なポイントと考えております。
As we have seen in the interview, manufacturing has become more complicated than ever in accommodating to various needs. But our required cost reduction even though work processes are increasing, and we are under the pressure to transform to new manufacturing. Now, we would like to introduce specific examples of the new manufacturing with the 4 parts used in medical equipment. First, let us introduce 2 cases for the clinical chemical analyzer. For the first case, we'll take the aluminum partitions used inside the frame as the example to show how we can reduce machining processes. In this example, we replace the machining process of 8 mm thick aluminum part to sheet metal processing by using 2 sheets of 4 mm thickness each. Please take a look here. The 2 sheets are laminated, and by making holes and notches in just one sheet, we can make the same shapes with the sheet metal processing. Over here, we use the laminated structure to insert a nut between the 2 sheets to replace the tapping. The hexagon counter bore is made during the blanking process. It is processed in 3 steps in the order of pre-hole, pressing, and size finishing. When you see how it is processed in animation, it looks like this. The first step is making a pre-hole. The second step is pressing the sheet thickness with a special hexagon tool. The pre-hole made during the first step is made to prevent the material from deforming during this pressing process. The third step is fixing the hole size to complete the hexagon counter bore. Also, high upward half-shear forming is used so that the 2 thick sheets can bond well. Generally, for upward half-shear forming, the top tool diameter is larger than the bottom one, but it is breakable and cannot form high. So by making the bottom tool diameter larger than the top one, it is less breakable and permits high forming. By incorporating all these processes into the blanking process and eliminating the machining process, the lead time can be reduced significantly. For the second case, we will take the small bracket as the example to show how we can improve the bending efficiency. Its characteristics are the many complicated shapes, and it is often difficult to bend due to unstable gauging. The operator tends to get very cautious and takes long time for bending. The new bag gauge comes with independent move to right and left, front and back, which can provide speedy and stable gauging for complicated shapes. Until now, this part could only be gauged at one point, but it can now be gauged stably by 2 points to allow for speedy and easy bend. Next, we'll take the CT frame as an example to show you how we can improve the efficiency of the welding process. Please take a look at this piece here. The weld portion is very long, and with traditional methods, the heat will likely deform the material, so it requires higher welding skills. By replacing this with the latest fiber laser welding that can limit the heat effect during welding to a minimum, we can reduce the time for deciding the welding order, tack welding, and correcting the distortion. Very effective for shortening the lead time. When our shape is being welded, the sufficient 50-50 weld overlap is necessary, which is very difficult with positioning tool overlapping. We would like to introduce you an effective way to positioning welding overlap: the addition of tabs and slots that are half of the sheet thickness. Tabs and slots are made during the blanking process. They are processed in 3 steps, in this order: 1. Square hole processing, 2. Pressing, and 3. Laser cutting. The first step is making a square hole. Second process is pressing with a special tool. The square hole in the first process is made to avoid the material from deforming during the pressing process. The third process is cutting the profile into tab shape with a laser. This positioning method not only speeds up the positioning process, but improves the precision as well. Next, we would like to take the test operating panel as an example to show how we can improve the efficiency of the welding process by integrating parts. This product, with such shape, consists of 6 parts, and since they are mostly welded together, it takes time to assemble. Here, we will integrate those 6 parts into one single body piece to reduce the welding process. First, the corner parts with the radius are combined with the sides, and the R shape will be changed to a bending process. The front section has a difference in level of about the material thickness for mounting the panel. Until now, these parts were welded together. We eliminated the welding by changing to endless Z-bend during the blanking process. Now, those 6 parts become one single piece body. Endless Z-bends make level differences by feeding pitch. A variety of shapes can be made depending on the program. As a result, the weld sections are reduced from 13 to 8. Furthermore, the position of parts for welding are also reduced, so we can expect significant lead time reduction. Last is the artificial dialyzer. We will take the internal frame for an example to explain how we can improve the efficiency of the assembling process. The artificial dialyzer has many parts inside. Therefore, checking the position and the direction of assembly is an operation that takes time, and it often leads to mistakes. Laser marking are made to eliminate assembly mistakes, top and bottom, left and right. Tabs and slots are being added. This reduces the assembly time and assembly mistakes. Lastly, we introduce you our latest blanking, bending, and welding solutions that can utilize the processing technologies we have just introduced. FLC, the fiber laser machine with a high speed, high accuracy cutting of all metals, including stainless steel and aluminum. Akias, the punching and laser combination machine for integrating multiple processes into the blanking process, and reaches high-grade automation. HG, the high accuracy, eco-friendly press brake, is designed for high productivity for complicated shapes and R-bands. Also, we introduce you another press brake, EG, the compact electric servo bender. FLW, the fiber laser welding solution, is for realizing high-grade processing, challenging the boundaries of welding processes. We have introduced you our leading-edge processing technologies as solutions that realize new manufacturing today. Amada has been working for a system to reduce the lead time of high value-added products without depending on skills in all process stages. Amada's new manufacturing will drastically change sheet metal processing. We will continue to work with the customers in solving manufacturing issues. Thank you very much for your audience.